How would these new cylinders perform, not under extreme heat, but under tremendous explosive force? The next set of tests answers this question. As a reference point, here's what 1/2 stick of dynamite does to a 24-inch diameter granite boulder in slow motion.
Clear the area! Make way for the blast! Fire in the hole! Fire in the hole!
Almost 350,000 foot-pounds of energy fragment the boulder in all directions. And this points to another advantage of aluminum. Even when aluminum does give way to such force, it is not as likely to fragment as this boulder or steel could. The first 3 tests you'll see were performed at ambient temperature. 1/4 of a stick of dynamite will generate approximately 175,000 foot-pounds of energy. The dent created was approximately 13 thousandths of an inch into the metal, equivalent to the thickness of about 5 sheets of paper. The 1/2 stick dynamite produces approximately 350,000 foot-pounds of energy, with the equivalent of a car impacting into a wall at 40 miles an hour. Calculations were done by a major car maker. The dent developed from a 1/2 stick of dynamite was less than 1/16 of an inch. There was no damage after cylinders were exposed to dynamite. A number of them have been subjected to hydrostatic burst tests. In both the 1/4 stick and 1/2 stick tests, the cylinder exceeded 5,000 psi, which is the test pressure of the container. And last of all, a full stick. This is energy equivalent to a car impacting a wall at approximately 89 miles an hour. It is particularly noteworthy in this test that while there is gas venting, it is venting through the valve and relief device. The blue arrow above the cylinder marks the spot where the dynamite was placed. What actually happened is that a shock wave from the dynamite, an instantaneous pressure spike on the order of 8 to 12,000 psi, created a deflection in the valve, causing the upper stem to move away from the seat, and the relief device was ruptured. But even though there was gas venting and a flash fire caused by a dynamite explosion, there was no ignition in the natural gas at any time. The cylinders contain the equivalent of approximately 5 3/4 gallons of gasoline, and a comparison should be drawn here to the amount of time it would take for a gasoline fire to be extinguished, whereas the natural gas simply vents safely into the atmosphere. Even if the natural gas had ignited, the only area that would have been affected would be on the periphery of the natural gas cloud. This is because 100% natural gas cannot burn. The next 3 tests subject the cylinders to the same explosive power, but at extreme low temperatures. These temperatures were created by packing the cylinders in dry ice for approximately 8 hours, thus reducing their temperature to about 100 degrees below zero. The result is a drop in the pressure of the cylinder from 3,000 psi to 1,100 psi. These low-temperature tests point to another advantage of these cylinders. Aluminum increases in both strength and ductility at low temperatures, whereas the embrittlement temperature of carbon steel is approximately minus 65 degrees Fahrenheit. This is particularly the concern for motor vehicles operating in northern latitudes, such as Edmonton and Alberta, Canada, and Alaska. And again, at a full stick and extreme low temperatures, the cylinders stayed intact and the gas did not vent.